Dear students, welcome to Experimental Techniques and Material Characterization, lecture number 8. In this lecture, we will continue our discussions on scanning electron microscopy. This is part number 8 in last part. In this lecture, we will have our discussions on the image contrast and scanning electron microscopy. So let's proceed about towards today's lecture. This is image contrast. So here you can see different images, that is secondary electron images. First of all, let's try to clarify the concept of the image contrast, that what is mean by the image contrast. So here you can see the images, and here you can see some two spectrum. So image contrast that we denote by C is defined is defined mathematically as C is equal to SA minus SB divided by SA. So now we will define what is what represent S and SA and what represent SB. So that is equal to delta S divided by SA. So here in this formula, SA and SB represent the signal generated from 2 points. So here you can see in this spectrums, in which the signal is being plotted versus the pixel. So here we have 2 points depend upon the signal, that is a point signal A, this denoted by SA, and signal at point B is being denoted as SB. So A and B in the scan area, so it's represent the signal, that is signal at area point A and then point B. So in order to detect object of small size and low contrast and in SEM, it is necessary to use a high beam current and a slow scan speed. That is to improve signal to noise ratio, which you can see here. And this is the secondary electron topographic and backscatter electron atomic number contrast. So secondary electron image, that is topographic contrast. So here you can see two different images that is being taken with the help of secondary electrons. By using the secondary electron feature in SEM. So here you can see that this one, this basically show defect in a semiconductor device. Here you can see that that we have a debris that is an oxide fiber which got stuck in the semiconductor device, and that is being detected with the help of scanning electron microscopy. And this one is the molybdenum trioxide crystals. So here you can see the fine crystal structures of molybdenum trioxide crystals, which is being obtained. The micrograph is being obtained with the help of scanning electron microscopy. So backscatter electron image, that basically mean that with the help of this we can get the atomic number contrast. So here you can see in this micrograph, it is the backscatter electron atomic number contrast image. So what actually it shows? So it shows niobium rich intermetallic phase, that is the bright contrast. You can see here the bright contrast. So the bright contrast has been dispersed in aluminum matrix, that is a dark contrast. So basically this micrograph is an ally of niobium and aluminum. Along with that, we have oxygen. So beryllium, oxygen, and aluminum ally. So this is an ally. So the dark one, it corresponds to one particular atom, and the bright one is correspond to another particular atom. So here you can see the different the atomic number for niobium, the atomic number for aluminum, and for the oxygen. And we have, you know that oxygen react with the aluminum. The oxide of aluminum, we basically, the most popular one is aluminum. That's how we have the atomic number contrast with the help of backscatter electron image and the scanning electron microscopy. Another feature is in the contrast we have field contrast. So electron trajectories are affected by both the electrical and magnetic field. So electric field, the local electric potential at the surface of ferroelectric materials or a semiconductor PN junction produce a special form of the contrast that we call voltage contrast. Magnetic field, imaging magnetic domain. I mean, with the help of the magnetic field, what actually we do with that? With the help of the magnetic field, we produce imaging magnetic. I mean, we're trying to get the picture of the magnetic domain with the help of the magnetic field. So here is a good example. I mean, of the voltage contrast. So here you can see it in this micrograph. So what actually it shows, and what are the sort of the information we get. So it's a voltage contrast from an integrated circuit. So this is an integrated circuit that is being recorded at 5 kV. So the technique gives a qualitative view of static potential distributions, but by improving and the instrumentations, it is possible to study the potential which may be varying at the frequency up to 100 megahertz or more, and to measure the potential with the voltage resolutions of plus minus 10 millivolt and a special resolution of 0.1 micrometer. So what actually this image show? So here you might be wondering that what sort of information we get, and what is this image basically stand for. So this image, if you observe it clearly, so it shows a hard piece microchip power up and running, but removed from its usual protective casing, which is being examined in the SEM. In addition to the normal topographic contrast, a large-scale region of uniform, bright, and dark contrast are visible. Here you can see that it's bright and dark contrast. It is separate. I mean, you can separately view it here. So the bright areas are those. The bright areas here you can see that these bright areas. So they are those which have potentials which is negative, and we have denoted it by minus U with respect to the ground, while the dark areas, I mean here these are the dark areas, are positive. They have positive potential that we have denoted by positive U with respect to the ground. So the origin of such a contrast is straightforward. So when an area is negative, then the collection feed from the secondary electron detector is increased, and a higher fraction of the secondary electrons are collected. An area that is positive experience a lower collection field from the detector, and also has a tendency to collect its own secondary electron. So the secondary electron signal from such an area is lower. This unique ability of the SEM to measure voltage and the real time from small areas and without requiring any mechanical contrast has been of considerable value in the development of semiconductor technology, and represent a significant fractions of usage of this instrumentation. So another feature, another type of the contrast that we can get with the help of scanning electron microscopy is called magnetic field contrast. So here you can see we have two images or two micrographs. So these are basically the high resolution SEM images of the magnetic microstructures in an ultra thin wedge shaped cobalt film. It's an ultra thin wedge shaped cobalt film. So what actually we get or what actually it shows. So secondary electrons emitted from a clean surface a ferromagnet are spin polarized. The sign of the polarizations being opposite, which has been shown with the arrows directed in opposite directions. The sign of the so the magnetization vector in the surface uh, here uh, the sign of the polarization being opposite to the magnetization vector in the surface of the material. So what are the informations that we get from both of these micrographs? So here, if you observe the pattern, so I mean it can clearly indicate the transitions from a preference uh, to the vertical directions for film that are thinner than about 0.6 nanometers at the bottom, to a planar structure for a thicker film that is at the top. So the two different magnetization component, I mean here you can see it easily at point, I mean at figure A and figure B. So at figure A we have mostly, I mean the vertical, it's a vertical sense, and the B is parallel to the thickness gradient. Both of these are made visible by electron polarization analysis and different detectors. For the image showing a domain obtained from the perpendicular component of the magnetizations, that is, I mean here you can see at the bottom of this figure, and the same thing that you can see here at figure B at the top. So the light areas, I mean, which is here at figure 1 at the bottom, and figure B at the top, it indicates the domains with the magnetization pointing out of the image. I mean here, I mean it represents the domains that are representing. I mean so it's pointing out of the page. Black areas are the domains. I mean here inside this, the black areas, I mean inside this, I mean we have two sort of the areas. One is the brighter one and one is the darker one. So the brighter ones, they're basically domains pointing out of the image, and black areas are the domains with the magnetizations pointing into the plane. So the gray tones represent areas. I mean here you can see the gray tones. I mean at the top here at figure 1 and at the bottom of the figure B. So these gray tones represent areas with the vertical polarization components and between. Other imaging modes consist of cathodoluminescence, that in short we call CL. So it's a non-destructive analysis of impurities and defects and their distribution and the semiconductor and luminescence materials, and it has the lateral resolution. I mean this kind of feature of scanning electron microscopy is mostly adopted to find out the defect structures and to find out the luminescence characteristic of a material. So it has a lateral resolutions that is approximately equal to 0.5 micrometers. And with the help of these features, we can get phase identifications and rough assessment of defect concentrations. Another most popular feature is called electron beam induced current, that in short we call ABEC. So what is the use of that? This kind of feature is only applicable to semiconductor. So you know that in semiconductor, once you apply that, so in semiconductor we have electron hole pair. They are being generated in the sample when we apply this technique. So external voltage applied, the pair are then the pair then move in the form of the current, which is being amplified to a given signals, and these signals they require information about the sample. So with the help of this feature, that is electron beam induced current, or that in short we call the ABEC. So with the help of this technique, we get image defect and dislocations and a sample. So here in this figure you can see it's a CL micrograph of the tellurium-doped gallium arsenide. So these are I mean A and B, they are basically the CL micrograph of tellurium-doped gallium arsenide. So at A, at sample A, you can see that the tellurium concentration is 10 raised to power 17 per centimeter. So the dark dot, I mean here you can see the dark dot, I mean it's the dislocation contrast. And figure B here you can see that here the concentration of the tellurium is 10 raised to power 18 per centimeter cube. So the dark and the hollow, I mean here you can see the dark and the hollow dislocation contrast, which shows variation and the doping concentrations around the dislocation. Avic image of doping variations and gallium arsenide wafer. So here again, is the image, the Avic micrograph of the doping variations and the gallium arsenide wafer. So here you can see the variation in the brightness across the materials, and it's because of impurities in the vapor. I mean here you can see we have darkness, and we have dark and bright locations on the vapor. So it's a complete vapor. We clearly analyze it. So here you can see the bright and dark areas. So it's basically due to the impurities in the vapor. The extreme sensitivity, that corresponds to 10 raised to power 16 per centimeter cube, or 1 for in 10 raised to power 7. So the extreme sensitivity and speed of this technique make it ideal for characterization of as-grown semiconductor crystals. What it means? It means that ABIC is one of the best techniques to find out about the impurities in a semiconductor material, especially in that particular case where you're trying to dope one kind of the materials into another kind of materials. I mean, if you want, you apply the techniques to grow a material, and then you want to dope some other material in order to enhance or change the properties of the materials. After that, once you're done with the experimental process, you want to check whether the material has been properly doped or not. So that can be done with the help of the ABIC. So with the ABIC, you can find out your doping material inside the material. But we remember this technique is most suitable for the semiconductor materials. So that's all we have for this lecture. So with this, the lecture on the scanning electron microscopy has been over. So in next sections, we will start discussions on another techniques. So stay tuned for the next lecture series on another microscopy that's been utilized in material characterizations. So stay tuned for the next lecture. Till then, bye bye.